Hi everyone, welcome to the talk. I'm glad to share our NDSS 2022 work here, titled Progressive Scrutiny, Incremental Detection of UBI Bugs in the Linux Kernel. I'm the first author, Yizhuo from UC Riverside, and I'm working with Rikans and Zhiyun. This is a joint work by UC Riverside, Penn State University, and US Army Research Lab. So first, why do we need such incremental detection? Some background before we are answering this question. As we know, Linux kernel community has a rapid development cycle. They release the mainline stable versions roughly every 2 months. Among this time, each release candidate would be published every week. Once the stable version is released, they would create a new repo and maintain the stable version separately as a minor versions. And on average, there are 10 commits per hour that submitted to the Linux develop tree. Those commits introduce the new features, the bug fixes, not intentionally but inevitably some new bugs into the system. Due to the rapid development cycle, developers usually do not have time to conduct thorough security checks before committing new code. Unfortunately, once a bug is introduced, it can take people a long time to catch the bug and fix it, especially for downstream distributions. For example, a Linux maintainer reported that the average lifetime of kernel bugs in Ubuntu from 2011 through 2016 is 3.3 years for critical bugs and 6.4 years for high-severity bugs. This provides ample time for adversaries to discover and exploit the vulnerabilities. To mitigate those security risks in the Linux kernel, both dynamic analysis and static analysis have been applied. Dynamic analysis, specifically the fuzzing approach, is currently the most popular and effective approach to find bugs in the Linux kernel. With the state-of-the-art kernel fuzzer syscaller and help of various sanitizers, thousands of bugs have been discovered in the past few years using the continuous fuzzing platform maintained by Google. And plenty of the static analysis tools are developed. Those tools can be divided into 2 categories. First are some tools to detect specific bugs. They would use some chain analysis or pattern matching approach to find one kind of bug. The second categories are some general framework to detect some specific modules, which is more general but hard to be scalable. Given such rapid development cycle of the Linux kernel and the number of commits every hour, the drawbacks for those 2 approaches appears. For the fuzzing, and actually all the dynamic analysis, it has the problem of incomplete code coverage. If the code is not executed, then it's hard to verify those part of the code. And for those incoming code, it's hard to generate the input and analyze them exhaustively. Regarding static analysis, it seems a perfect way to analyze those code exhaustively and does not require a concrete input to exercise the new code. But the precise and scalable analysis takes a long time and hard to fit into the development cycle. So the problem comes, we would like an approach to exhaustively test the code, while we need such analysis to fit into the kernel development cycle. As we can think about, and it is, every time the code change just occupies a small portion of the Linux kernel. For example, from Linux kernel version 4.14 to Linux kernel version 4.15 RC1, there are only 4% of the function changes. Therefore, the idea comes, would it be possible to do a whole program analysis once and record the result, then incrementally analyze only the new introduced code instead of starting over? If that works, we will have several benefits. First, we would have a quicker turnaround time for each analysis and make the precise analysis fit into the development cycle. Further, if we can do this for different versions, we can also do this for each commit. For example, we would have a quicker validation of new proposed patches. This is important because currently, after a new patch is proposed, the kernel community heavily relies on manual inspection, email changes from peers to spot potential bugs, which is time-consuming. Third, because incremental analysis is based on static analysis, it provides an exhaustive coverage unlike what dynamic testing can offer. So how can we do that? Let's look at a previous bottom-up summary-based analysis tool called UBI. I'm the first author of this work also. This is a whole program analysis tool to detect use before initialization bugs, and it combines the qualifier analysis with under-constrained smart execution to detect use before initialization bugs in Linux kernel. The picture in the left shows a UBI scenario. A variable first declared without initialization. Then in some paths, it is It lived uninitialized, then got used. The UBI tag first detects such problem and then records some related information, basically the basic blocks that affect the initialization status. Then based on those information, UBI tag uses under-constrained execution to explore the feasible path. If there is a feasible path between the uninitialized variable and its use, then we generate a corresponding bug report for it. This detection is precise as it uses the field, context, flow-sensitive, and inter-procedure analysis, and also is scaled to the whole Linux kernel. The key point to make such precise analysis scalable is a bottom-up, summary-based analysis. It first builds a call graph for the whole kernel, then did a topological sort for all of these functions. Then it starts from the leaf function, analyzing it, and then record a summary of the function. Later on, when it analyzes its caller, instead of analyzing the calling again, UBI tag will refer to the summary and did the analysis. In this way, every function analyzed the minimum amount of times, and thus make the approach scalable. Let's take a closer look for the function summary. Here is an example. Function f3 is a leaf function and accepts two arguments, an integer a and an integer pointer pa. Then this function would initialize the object of pa into a constant. It uses a as the if condition. When UBI tag does the analysis, it finds out that the pointer pa is dereferenced. Therefore, if this function call wants to be UBI bug-free, then its caller should pass an initialized pointer when it does the function call. So we listed this in the requirement, showing as the requirement for PA is initialized, and anyway the object of PA would be initialized. So we record this info as updates. And for A, function f3 directly uses argument without the initialization. In the same way, the caller should pass the initialized A into f3. For return value, f3 returns a constant, which is an initialized value. Now we have the requirement and update. Then if we analyze f6, we do not need to analyze function f3 again, but instead, we can refer to the summary and update the initialization status of variables in f6. Now after using UBI tag, we have a bunch of function summaries. When the new code comes, we got the chance to analyze the functions that are only affected by the new code. Here's an example to show the incremental analysis. In the new version of the code, the F4 are modified. We first analyze F4 and get a new summary called FS4 prime. Then we compare the FS4 with the FS4 prime. If they are equal, then we are done with the incremental analysis. In this case, we only need to reanalyze F4 in the new version. On the other hand, if FS4 does not equal to FS4 prime, then we go ahead to reanalyze and resummarize its callers. We will not stop until the caller summaries are equal to the previous version. Now let's look at the whole workflow we designed named Incremental. We have a new version and previous version of the kernel. We first did the pre-processing, including the diff function extraction and call graph analysis for the new version of the code. Then we got the calling relations and SCCs. SCC stands for strongly connected component. In such SCC, the function relations form a circle. The input also include modified function and previous function summaries from the last analysis. Then using those input, Incremental conduct the bottom-up summary-based analysis. It first reanalyzes and summarizes a modified function, then it compares if the function summary is the same as the previous one. If not, it go ahead to analyze the affected callers until the summary does not change. After analyzing the function, it generates warnings. After such bottom-up analysis, we got the new summaries and new warnings. With those new summaries and new warnings, we use the UCSE to explore the feasible paths and generate bug reports. By comparing the bugs with the previous one, we have some bug differences, indicating some bugs are introduced or fixed. For implementation, our framework is based on LVM 9.0.0 and we use CLI as the UCSE engine. Here comes our evaluation. We use the version 4.14 as a baseline to do the whole program analysis. And then based on this set of function summaries, we continuously conduct an experiment for version 4.15 RCs to version 4.19 along the mainline stable version. Then we jump to version 5.4 and version 5.9 to test the effectiveness of such big gap. And also we do the incremental analysis for version 4.14 and version 4.15 stables. As version 4.14 has more than 220 versions, we pick every 20 versions. We also pick some patches to do the per patch analysis to check if our incremental analysis can achieve the same result as whole program analysis. We conduct the equivalent analysis. From those analyses, I will show you the speed improvement, time breakdown, the bug finding result, and patch identification result. First, for time speed up, overall, we have 3.78 times to 800 times speed up for mainline versions and 11.04 times to 32.29 times for version 4.14 every 20 minor versions, and 32 times to 800 times for version 4.15 minor versions. The details are listed in the table. I put the mainline version here for example, and all the details can be found in the appendix. Given such analysis time, we record the time split for each step from version 4.14 to version 4.15 RC1. This pie chart shows the time breakdown for each function. Incremental follows the same analysis time steps in UBI tact as pointer analysis, alias set generation, qualifier inference, and summary generation. We see that the most time cost phase is the alias generation, followed by the point 2 analysis. Then the qualifier analysis and function summary generation takes a small portion of the incremental analysis. To confirm the factor which affect the analysis time, we draw the relations between the number of functions analyzed and analysis time in this figure. As we can see, the cumulative analysis time is proportional to the number of analysis functions. Here's the evaluation for per patch analysis. We collect the patches from UBI tact, and results show that Incremental can quickly finish checking those patches, showing that the intended bugs was fixed and did not add new UBI bugs, except for the first patch, which took half a minute to finish. Other patches were checked within 5.46 seconds. We believe this quick feedback can be extremely valuable for kernel development. To evaluate Incremental's ability for bug findings, we randomly sample 44 bugs reported by it, and 22 of them are true positives. 5 of them are dismissed by maintainers because the condition to trigger those bugs cannot be satisfied in reality. For the rest of them, we found that 7 of them have been fixed in the later mainline. We have reported all unpatched bugs to the maintainers. 5 has been confirmed. The bugs are listed in this table. Regarding the Incremental's false positives, it has the same false positive reasons as UBI tags, such as incomplete guidance and inaccurate indirect call resolution. If one bug disappears in the new version, then it indicates there is a bug fixes in the new version. Incremental can help developers to reason about whether the patches can work as intended. In this evaluation, we track the confirmed bugs reported by both Incremental and UBI tact. It turns out only 2 bugs are patched within this range, and Incremental correctly identified them. For false positives and false negatives in bug findings and bug fixes, please refer to the paper for details. A key requirement for incremental analysis is that we want the same result as the clean slate whole program analysis. To evaluate this, we perform whole program analysis for this kernel version 4.14.20 and version 4.15, and then compare the bugs reported with those reported by Incremental. The results show that we have the same warning set in the whole program analysis and Incremental. However, in the warning validation phase, due to Klee's non-determinism, although we do not have difference in version 4.14.20, but one bug is missed by Incremental. To eliminate such difference, we can put more computing resource to Klee. To conclude, in this paper, we propose Incremental, which is a framework for principled incremental analysis for Linux kernel. It can dramatically speed up the analysis time compared to today's expensive whole program analysis and fit into the kernel development cycle. It effectively identifies bugs and bug fixes, making it useful for real-time feedback and help test the bug fixes. Finally, the tool is open sourced in GitHub and welcome to try and contribute to it. Thanks for attending the talk, and I'm happy to take questions.